So we'll start. It's yeah. Okay. We can always accelerate. So it seems I have to finish in 45 minutes, so that we go for lunch. But I will try to. So method of oscillating test functions. Ah, okay. So this was introduced by Tartar. Okay, and somewhere mid 1970s. Okay. So what is this and why do we need this? So let's start with whatever problem. So I am in the scalar case, not in the elliptic case. Things are easy to explain and simple there. So we look at this same second order elliptic problem. I will take F epsilon also on the right hand side. Okay, we take this scalar problem and as has been since morning, A epsilon is L infinity and is also elliptic. And in this case, it is uniformly like the ellipticity is independent of epsilon. It's uniformly elliptic. Okay. No, I'm not assuming that yet. So I will do the periodic case as an example. That's what I was telling Shivaji, that I prepared the general case because you said 1.5 hours or something, and later, so now I'll reduce it to, I'll give the periodic as an example. Okay. So far there is no periodicity. A epsilon is, this is for all psi in Rn and almost everywhere x in omega. Okay. So, and we have, I'm assuming that we all know that there is a weak formulation and we have this estimate on the solution, which is H1 0. If, and I'm assuming that F epsilons are in, I'm assuming F epsilons are strongly converging in H minus 1. Okay. Somewhere. Yes, that's what it is. It is uniformly bounded and uniformly elliptic. It's independent of itself. So because of that is why you have this estimate. My handwriting is bad on this tablet, but it's okay. If it was anyway bad, it's worse here. So we have this bound, okay, in H1. So which means up to a subsequence, you have a U naught in H1 0 omega. So it's for a subsequence, but to avoid too many notation, we will use the same epsilon. This convergence is weak in H1. So, and now if you look at the weak formulation of this problem, let's call it some star. And we also have the other boundedness, which is about this boundedness. Let's call this xi epsilon. So xi epsilon is A epsilon grad u epsilon. This is in L2. This is in L2. This is L infinity. So you actually have the sequence bounded in L2, and hence you also have a xi0 in L2, such that A epsilon, which is I epsilon, converges weakly to psi naught in L2. Okay, we have these just from the assumption that A epsilons are L infinity and it's coercive. And because we have also assumed that F epsilon is bounded in H minus 1, this is also bounded by some constant, independent of epsilon, right? So now if you use the variational formulation of star, okay, and then pass to the limit. So in other words, you have A epsilon, grad U epsilon, let's say grad phi in omega is equal to F epsilon phi for all phi in H10. Okay, so we can, so this is the weak formulation of the star problem. So we can pass to the limit here. So as epsilon goes to 0, you actually have xi naught grad phi f phi, which gives us the equation, okay, so let's call this equation double star. Okay, so now you see we had the star equation here. We have something A epsilon grad epsilon equal to F epsilon here. And also the boundary condition is also satisfied because U0 is in H10. So you also have U0 is 0 on the boundary of omega. So this is in omega. Now the question comes is, can I write xi0? Is it possible to write? I mean, is it possible to relate xi naught and U naught? What is the relation between xi naught? Because U naught is the solution coming, I mean, U naught is the limit of U epsilon here, right? Here. And then we have a xi naught. So can we relate, or more particular, can we say there is some matrix A naught such that I can write xi naught as A naught grad naught, so that grad U naught, such that this equation becomes A naught grad U naught F with U0, 0 on the bound. So is it possible to do this? Okay, that's the question. And that's where the method of oscillating test function comes in. Okay, so the idea is, so first I'll do the easy part, because the difficult part is actually constructing the test function, which I'll come to the, which is the interesting part, which I'll come to after. So suppose we know that we can construct a test function like Tartar did, then what happens, right? I'll just quickly show that. So what does Tartar say? That to answer this question here, he says you can find a sequence which is the oscillating test function. Let's call it W epsilon I. So you can, so this you can do for each I. So for me, dimension is n. Omega is in Rn. So it's, and I is from 1 to n. So for each I, you can construct a sequence, okay, W epsilon I, and you can also find a naught, okay, and the way a naught and W epsilon I are related is that, in fact, you have this equation. I think I would want with transpose. I have not assumed even symmetry of A. So transpose grad W epsilon I equal to A0 EI. This is in omega. Okay, it has this relation. And in fact, on the boundary also, it can satisfy Xi. Okay, now this, so this is the main part. Okay, this is something I will tell you how to choose this later, okay, at the end of the talk. But suppose we have this, then we can relate psi naught, and with that A naught, psi naught, and U naught. Okay. So that part is easy. So I'll quickly finish that part of the proof, which is just algebraic thing. Like you just use the. So what we do here is that you notice first that W epsilon I for each I is actually an H1 omega function. Okay. You have this property that it converges weakly to Xi in H1 of omega. And you also have, so these are properties which are just outcome of if we do whatever I have said here. It converges to A0 EI in L2. And you also have that this sequence is strongly converging in H minus 1. Okay, this sequence is strongly converging in H minus 1. Okay, to something. And in this case, we know what it is. Okay. So we have these properties about W epsilon I. Okay. So using this, and since W epsilon I is so since W epsilon I is just an H1 function here, it's not vanishing on the boundary of omega. Yeah. What is the? Oh, you and no, that's the transpo IV, because there are too many subscripts. Why the? Xi is so X is the the ith projection of if X is an element. So Xi, I'll show it to you. So that is how it is constructed, because you have here EI. So EI is actually gradient of Xi, like that, right? So okay. So I will show the example in the periodic case, but it is just coming from this equation. The way you choose W epsilon I and A0, all this property will be satisfied. Okay. In fact, W epsilon I is chosen using this projection map, from X to Xi, and then do some lifting. Okay. I'll show that after I finish this easy part. Okay. So where was it? So now our aim is to use this. So this is Tartar's oscillating test function. Okay. How to choose this is the entire crux of the thing. Okay. But once we do this, then it's easy to relate psi naught and U naught. via A naught. So how to do that? You choose a, in fact, I don't, I think d omega is fine. I can choose H10 also. So d omega and then phi, this is in H1, 0, okay? Now you use this as a test function in the original equation here, in this star. Okay, I use phi w epsilon I as a test function in star. So what do we get? So I should get f epsilon grad phi w epsilon I. Huh? This one? It is? Yeah, he doesn't write it in the. Xi epsilon. Xi naught, yes. Yeah. No, no. So here. Yes, I have not come to that proof yet. I don't know A no both. Fine. I'm going to construct. Yes. 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 If you want, I can explain. I can go to that proof now. No, no, I will not use. I will not use I naught. I will not. Okay, I can. I can stop here. I can come back to this. No, no, it's good. It's good. It's good to. It's good to do it now itself because since the question has come. Let's do what Tartar does. Okay. So Tartar. So for that you start with this operator, right? So I'm going to look at the transpose operator. Okay. MFs. Look at this. So and he actually works not in omega because omega you are on boundary, so you have to go outside. So you look at some open set containing omega. You take a bigger set O, okay, and you let me define a matrix M epsilon, which is transpose of A epsilon. Whenever you are inside omega. And when you are in the outside complement of omega, you just extend by alpha I, where alpha is the ellipticity constant of A epsilon. Okay. So you do that, M epsilon. And now you look at this operator. T epsilon minus divergence M epsilon grad. Okay. To take this T epsilon. This T epsilon, now you can think of, this is actually an isomorphism from H1 of O to H minus 1 of O. Okay. So now the idea is that you look at this, you define for PI. PI is the, so you have to choose a test function also. So I'll choose a test function. Let's choose a phi in d omega, and later we will choose a specific phi, no, not d omega, and do. Sorry. Okay. And later we will choose a test function phi, which becomes 1 on omega and outside, so that we get back to whatever we wanted. So you start with, yeah. No. H1. Okay. Because originally, see, because I have extended here this M epsilon, so I have said This is in the complement. No, so I because here it is an I mean you can still Laplace and still an operator from H1 and to I mean you can I mean what do you do for Neumann condition for instance? You cannot. It's not isomorphism. It is a yeah. Yeah. O bar you can take. Yes, you can choose for bar. So, I mean, the reason I am introducing this is to just because instead of writing down the proof, I can show it in a picture. So, if you can think of, if I take, let's say, phi, and I look at, let's say, so if, let's say Pi x is equal to xi, okay, and then I look at let's say phi of Pi. Let's call this Fi. Okay. Now this Pi is actually in H1, but not in H10. Okay. So if I can think of, if I think of this as H10, I can think of this as H minus 1 O. So we start with a phi I Pi here, which is actually my Fi. Okay, so this is for each fixed I. Okay, and from here to here, I go via the what is so T naught is the so T epsilon inverse is because of the coercivity of A epsilon and hence M epsilon and so on. You can show that T epsilon inverse is actually converges in the weak operator topology. Okay, so by the compactness there, you have some limit up to some subsequence something. What we discussed now is not something. But here I just need the what is called. I mean the surjectivity of it. I can here I miss something. Sorry? They are using the surjective to write. In other words, you are solving the equation for arbitrary right-hand side without boundary condition. Is it? For the for T epsilon. For T epsilon without boundary condition. Yes. I'm just looking at like this, like I'm looking at this element and looking at this map as see this T epsilon is okay. Yeah. No, no. See, afterwards, we want to capture xi in the interior. Yes. And you can extend it to 0. Actually, phi, I mean, by what I'm doing with phi is precisely that. What I'm doing with phi is actually making it 0 outside omega. You can also do this. Yeah, once I put phi, because finally I'm using the isomorphism only in H10. Right? Because once okay, I should say that. Yeah, I should mention that. Once I use PIs, phi PI is actually in H10 of O. Okay. And now I use the T epsilon on H10 of O and I get T naught, okay, which is the weak operator topology limit. So I put T naught, okay. So I have a T naught. So this let me call this for convenience T naught inverse. So T naught is the inverse of that. So this is in H minus 1. So let's call this T naught of huh? Okay. So I want to say that T epsilon inverse of F comma G. I will precise what is, let's write it the other way because of the so G comma T epsilon inverse of F converges to G comma T naught inverse of F for all F comma G in H1, H minus 1 of O. Am I right? Because T epsilon is from T epsilon inverse is from H minus 1 to H1 from here to here. So I'm using. So this is the weak operator topology. Okay. Huh? No, I'm right because that will also be an operator from H1 0 of O to this. So I mean, so that will also be an isomorphism from H1 0 O to this. But I can, but yeah, I can go into that. Uniform electricity is there. That is there. Because that is where you have the G compactness. Eigenvalues then accumulate near zero. Yeah. So what is called the uniform coercivity of, so you can actually extract the subsequence which converges in weak operator topology only for uniform coercive operators. Okay. That is why I did not go into all that. That's why I pushed it to later. Okay, so now we have the limit T naught inverse. So the idea is this. So once we have T naught, we have. So if you don't like T naught inverse, just call it something, some T naught, and call this T naught inverse. That's it, right? So you have a T naught, which, so what you do, you choose phi pi, and you look at T naught of phi pi, and then you operate. Let me write it again. T epsilon inverse composition T naught of phi pi. This is W epsilon I. Okay. So what I am saying here, you start with phi pi, which is in H1. This is H1 0 O. Okay. You take the image under T naught. Okay. And then you take its image under T epsilon inverse. Okay. So that is the sequence. That is the Tartar's oscillating test function. This is the general case. This is the where you don't have periodicity or anything. So that's your W epsilon. Okay. And this is in H1. You can show that. And after that, you can choose phi test function such that it's 1 on omega. And you can get all that I want here. But I still have not defined what is A0 here. Right. So how A0 is defined is that once I have this W epsilon I, so now this quantity is bounded in L2. Okay. So up to a subsequence, you have a weak limit. It is something eta I. You define this as your A naught. Right. So eta I is obtained. So once I obtain W epsilon I, A epsilon is already given to me. So I know what is eta I, of course, up to a subsequence, which is why in the general case, you don't have a uniqueness or anything. Everything is up to a subsequence. And then you define A0 EI. You define A0 EI as eta I. Okay. So now if you go back, you can actually verify that whatever he constructed satisfies whatever I have marked in the red box. Since this needs some functional analysis and everything. I want to push to the last. So I wanted to do the FE part. So that's the general case. Okay, I can show. I will tell you the periodic case where things become much easier. Okay, much simpler here. So once we have, so this is the W epsilon I. Okay, for the general case. Now let's go back to. So now now let's use that as the test function in the star problem that we had. Okay. So what do I get by doing that? F epsilon here. Okay. You don't see when I show it, right? So F epsilon grad phi epsilon integral over omega epsilon grad u epsilon dot grad phi w epsilon I. Okay, we get that from the weak formulation. So now, if you look at, if you do the product rule here, this. So let me. I have already introduced that. So that a epsilon grad u epsilon is I epsilon. So I'll use that. So you have grad phi w epsilon I okay. And if I want the limit, we are on a, we have to pass to the limit here. But the issue is here that this is weak and this is also weak. So the product of weak convergence. So, but the way we have chosen our W epsilon I is going to complement this problem. Okay. So for that, what do? We look at this problem, the what I marked in the red square, red rectangle. You apply the test function here with phi u epsilon. Okay. That means to avoid, let me write down the direct calculation. So if I use in that red thing, I should get integral. So I'm writing the right hand side first. So right hand side, you remember I had divergence of A transpose EI. So that's grad phi u epsilon is equal to transpose of A epsilon grad epsilon I grad phi u epsilon. Okay, that is from that equation. That so I'm using the test function phi u epsilon in that. So let's call that triple star. Okay, so let's call this. I'm using this. I'm using the test function in this triple star. Okay, so I've written the right hand side. Okay, so now you apply your product rule here. Product rule here. You will see that. Let me. So let me keep it like this. We're not worry about it. Here I will have two terms, right? In this case, I will have two terms. One is with. Let me write down. Why be lazy? Okay, grad phi u epsilon and then plus grad u epsilon phi. But you now look at this term here and this term here. They are same, right? That's why we chose the so we are working with transpose precisely because I can bring it here. This is xi epsilon, which is exactly this term. So I can replace the term here with whatever I have here in this equality. Okay? Is that okay? So now let's do that. So I'm going to use whatever I have here in this equation, use it in this equation here. So I'm going to replace this term by whatever we got from the second equation. So if I simplify, you will see that f epsilon phi that's equal to less. So I replace this term with whatever we had there. So the terms I'm going to get are this grad phi u epsilon plus grad u epsilon phi dx, and then one more term okay. So what I've done is just replace this term using the equations here. So these two terms that you see here, these two terms are coming from the left hand side here, and this term with minus thing, this coming is actually this term. Okay. Now I can pass to the limit here throughout. So if I do that, on the left hand side, I will have f0 phi xi. Okay. And on the right hand side, you see, so this is strongly converging in h minus 1, so it's converging to f. This is fixed, this is product, and this is weakly converging in h1. So this is actually phi xi. Okay. So that is a strong and weak, so not a problem. Here again, this is weakly in h1, strongly in l2, and this is weakly in L2, so there is no problem. So you have xi naught grad phi xi. You will have the same here. There is only one term epsilon here, which is converging to u naught. Here again, this is converging to grad u naught weakly. Here again, this is strong and this is weak, right? So finally, what you get is omega plus integral over okay. So let's and plus transpose of EI grad phi, grad u naught phi minus okay. So this is what you get passing to the limit because everything was strong and weak. Okay. Now we already have this information that a divergence of xi naught is f. We had just done the weak formulation, right? You remember that when we started initially? Here, the double star. We already had the double star, right? So you can, if you use the test function phi w phi xi here, actually, right? Then you get whatever we had left hand side here. Here, if you use the phi xi test function, you will get this term on the, sorry, this is not f0, I'm using, it's just f, okay? So you get f xi, so this term comes from this side here. And you will have on the left hand side integral xi grad phi xi, okay, f phi xi. So the left hand side here can be replaced with this term. But this is with gradient of phi xi. But there is already grad phi xi here. That if it comes to the left hand side, what remains is xi naught, what is the term? Grad ei, and phi, right? Ei, phi. So that's what will remain on the left hand side. So on the right hand side, this has gone to the left hand side. What remains is here, but here you see this term is same as this term with the negative sign, right? So they goes off. What remains is just this. So what you have on the right hand side is integral omega ei grad u naught phi, or in other words, let me just write it better. Yeah, yeah, it's not very smooth for me. Yeah, dot ei. So this term I've taken the transpose with that. Okay, so I get a naught grad u dot ei into phi. This is valid for all phi. So what we have shown is that xi dot ei is a naught grad u dot ei. Xi naught is a naught grad u naught. This was possible by that choice of w epsilon I. Do I have time to do? Yeah. So I'll just do the, in the periodic case, like whatever Harsha had introduced in the morning, the cell equation, how this test function can be obtained, how this w epsilon I can be obtained from that cell equation. So there things are easier, much easier. Okay. So for time being, let's assume a epsilon x is a of x over epsilon. Okay, it's periodic. It's epsilon y periodic. So if a epsilon is this, then we look at the test function, which so Harsha said that that's the second most important equation to remember after the initial equation. So let's remember that and write down that equation. Let's minus. So that's the cell equation. So it's being written on the reference cell y. Okay. So reference cell y is the unit cube in Rn. Okay. So we write this equation for each I. Okay. That's equal to minus divergence y transpose of what am I writing? It's ay. Okay, transpose of AY EI. See, EI is gradient of uh, YI in this case, right? So you look at this equation, okay? This was given in the cell Y. What is Y? Y is equal to 0, 1, n, right? And we assume that chi I is Y periodic. I mean, that's the condition that you give on the boundary. So it's periodic boundary condition. And for uniqueness, you can assume the mean value is 0. Okay. So this is something which you already introduced. So engineers had known this uh, before, right? Because see, the entire purpose of doing this is whatever Harsha introduced in the morning, that engineers have been doing it for ages. They start with asymptotic expansion and they keep doing, they have the cell problem, they have been working everything. But for us mathematicians, that's not rigorous, because why should U epsilon admit a power series form in the scaling? But that's an intuition that engineers have to do it. Whereas what we have done so far doesn't make any such assumption that U epsilon has that kind of an expansion and so on. Right? Now, this problem, cell problem, taking motivation from that, I can just define in Y, right? Because once the matrix A is given, which is periodic, I can write down this problem. It's that, right? There is no issue, and we have existence theory for this periodic boundary condition and so on. Once we write that, to relate this with the Wi that was coming from the previous problem, so Wi of Y is chi I of Y minus Y dot EI. Okay? It is just this, because this is just gradient of YI. So I have just written WI is this. Right? Now, if you look, now you can actually go back as an exercise also you can do. You can go back and verify. In fact, now this is just on Y. But I want the oscillating test function for each epsilon. So what is Wi epsilon for each I? It's epsilon times Wi x over epsilon. Okay, just that. Now this W epsilon I will satisfy the conditions that I had marked with the red rectangle. Everything it's satisfied, and this test function can be used in it. But I have defined W epsilon I. What is A0 here? Right? A0 can be uniquely defined in the periodic case here. So we had seen in the morning. I mean, that proof is already there in the previous case, whatever we did so during Harsha's talk, where he gave the A0. So A0 EI, and I'll just write down the formula, and then A0 EI will be defined. In fact, I just need to define, I can transpose of A0 EI because I want to use this equation. So transpose of A0 EI will be 1 over mod this chi I of yi dy minus integral y ay dy, this acting on here. Okay, so how do I define a0 transpose? We have defined the cell problem. I have a chi I. We use this chi I to do this. This also can be motivated without even using the general case. If I don't want to do the general case, I can directly motivate this from here to here. Once I have W epsilon I, you just see what is gradient of W epsilon I. They are all periodic function. You know its weak limit. It will converge to the average of that function. A epsilon is also, periodic. So you have A epsilon grad U epsilon also will converge weakly, right? Finally, you will see that you can end up like this because actually these coefficients are constant now because once you integrate over y, these are constants. So once these are constants, you will actually see that in this problem, in the periodic case, the right hand side is actually 0. Okay, the right hand side is actually 0. So that's how you get the oscillating test function. Okay, I'll stop here, but if you want more details, I can do much more even later if you want. Sorry. How did you define? A naught in the general case or periodic case? A general case A naught was once I get W epsilon I, right? I can show you. So I get W epsilon I, right? By this choice. I start with phi pi. I can explain again if you want. So I choose a phi in DO. I look at phi pi. Pi is the projection x to xi projection operator. Now this is in H1 0 of O, right? So now what I said was you define W epsilon I, define it as T epsilon inverse of T naught phi pi. Okay, I said this, right? Once we have this, this is, one can show that it's actually bounded in H1 and will converge weakly to something in H1. So then this will have some limit weakly. Let's call it some eta I for each I, right? So I define A0 as this limit. I just say A0 is that limit, the weak limit. Okay? Yeah. Okay. Somewhere here? Yeah. 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 So this is weakly converging to transpose of A0 EI. From this equation, you can actually see that this is converging. What is the color? Transpose A epsilon grad W epsilon is converging weakly to transpose A0 EI. Because that's your. No, not from the. No. This is how I choose. So this is not a definition. I just gave you the proof of the Tartar where you do that. So that's how I chose my A naught. I chose my A naught. In fact, that's how I chose my A naught here. If you I just explained to you now. Here, I chose my A naught such that it's actually the weak limit of A epsilon grad W epsilon 9. So it will appear. Yeah. Parabolic. Parabolic? Okay.
Which the coefficients depend on T. Arbitrary. Usually, epsilons are coefficients are static. If you want to assume L infinity, uniformly elliptic, all those.
Okay. But depend on T.
Depends on. In that case,
okay.
In particular, this Tartar's construction, omega to O and so it was produced.
And maybe there we have to work with those Banach space valued map, no? Because I've not thought about it, but my guess would be that so the T epsilon that we took from H10 O to H minus 1, instead of that, maybe we have to look at L2 of the time variable. But that also I don't know with coefficients depending on. I have not thought about it. I have to think about it. Yeah.
XT.
No, T is also T over epsilon. Oh,
That's the picture. Wait.
then I think it will be. See, of course, I can think of T as another variable xn plus 1 and think of, but then point is about the, yeah, it's the point is about the regular, about the equation. You don't have the.
XT.
Yeah, I know, I understand. No, I know, sir, because for a parabolic, you don't have the, when you assume the time derivative, I mean, time coefficient, and you don't have the Laplacian component of time of that variable. Yeah, then I'm not. It's a good question to think about. Yeah.
So you have to talk about visual problem.
Yes.
So that's become for visual problem. You want to imitate these arguments.
For the homogenized coefficient there, yeah.
Or not.
Yeah, I have not thought about it.
Think about it, I did not succeed. Maybe you can.
Okay, I have not thought about it.
The important thing is that you must let the coefficients be as arbitrary as possible with respect to t variable.
Okay.
Arbitrary, that's important. But,
for the evolution equation, yeah.
okay, thank you.
Thank you.
So that's one.